Hello, this is Mr. Ferris. This is Lesson 7.1. Be sure to have the worksheet in front of you that looks like this, and follow along as we try to solve for the triangle that is given to you. You notice there's two sides and an angle. 82, 97, and side C. First of all, we need a little notation reminder that anytime you have a little letter C, it's always going to be directly opposite of side or of angle C. So we're going to let the angle across from side C be labeled capital C or uppercase C. And that will be the case for any sides and any angles. They will be labeled the same letter, but one will be uppercase, one will be lowercase. So lowercase c is always going to be directly across from uppercase C. So C is the angle, and C is the side. But uppercase C is the angle, lowercase c is the side. So let's let lowercase a be 82. That means that the angle directly across from 82 will be uppercase A. And 97 will be little b. Little b will be directly across from angle B, which will be capital B, uppercase B. So now let's see if we can solve the triangle. Well, we don't really know what kind of a triangle this is. It might be a right triangle. It looks like it might be close. But we don't know for sure what angle C is. So we have to have another rule. In fact, if we just let C be 92, then we know for sure it's not a right triangle. And therefore, we can't use the Pythagorean theorem. What we need is the law of cosines. This is a new theorem or a new principle, property, that we can use to solve this triangle, which has two sides and one angle. And the law looks like this. It's c squared equals a squared plus b squared. And if we stopped right here, you would think we wrote the Pythagorean theorem. In fact, that's exactly what we wrote. And that would be perfectly fine and would work for this triangle if it was a right angle. But angle C is not a right angle. So therefore, we have to adjust the length of side C because it's not a right triangle. And so that little adjustment for the fact that C is not a right angle is going to be added to our formula. And so the law of cosines will have another little piece minus the quantity of not A, but 2 times A times B times the cosine of angle C. That is the law of cosines for any triangle. It's called the law of cosines, of course, because we're ending with a cosine trig function. That's where it gets its name. So with this law, we should be able to solve this triangle. So here we go. Using the law of cosine, c squared should equal 82 squared plus 97 squared minus the quantity 2 times 82 times 97 times the cosine of 92 degrees. And 92, of course, is the angle. And since we're solving for side C, we always want to end with angle C. So if you trust me on my work here, c squared is going to equal 16,688 and a little bit. And then if we take the square root of both sides, we get to C is approximately 129.2 miles. So it worked. The law of cosines worked beautifully for this triangle where we were given 2 sides and the angle that's in between the sides. In fact, from geometry, you might remember that we labeled triangles many times with letters like side, angle, side. That's exactly what we were given. So therefore, the law of cosines is going to work really well for any triangle where we're given side, angle, side. It also happens to work really well for any triangle where we're given all three sides. So those are the two times when you would want to use the law of cosines. Side angle side and side side side. Problem number 2 is a good practice problem. I'll let you do that. Of course, we're going to have to adjust our letters because the letters are not A, B, and C. They are R, S, and T. Well, it's still two sides and the angle in between them. So it's still side angle side. So the law of cosines is the right law to use. But what we're going to have to do is kind of remember the relationship. Doesn't matter what letters you use, but the relationship is the key thing. So if you're using what I would call the C version of this formula, that means that C squared is going to be first and angle C is going to be last. So whatever letter that's used at the beginning of this formula is going to be the same letter at the end, except of course at the end it's an angle. So that's what we have to make sure we do, is keep the relationships the same. C goes with C, like that, but the first and last letters must be the same. And then the other two letters are just the other two pieces where you have A squared, B squared, and A and B again repeated after the two times. So it's a little bit of memorization, but there's also a pattern there that has to be consistent. So for this triangle, you just want to make sure that R, S, and T replace A, B, and C in the right places. All right, so let's do another practice problem. This happens to be a side, side, side problem because all three sides have been given to us in this triangle. This triangle is G, H, T. So let's label G in the bottom left, H at the top, T in the bottom right. And if that's the case, then side G will be opposite angle G, that's 6. Side H is opposite angle H, that would be 7. And side T is opposite angle T, which is 9. So we have side, side, side given to us, and we're supposed to use the law of cosines to find angle T. Well, if angle T is being solved for, that would mean that we have to put the cosine of angle T at the very end of our formula, which means by the pattern that T squared will have to be at the very beginning of this law. So T squared would be 9 squared. So 9 squared would be at the beginning, and then the other two sides, 6 squared and 7 squared, would follow that, minus the quantity of 2 times 6 times 7 times the cosine of T. So we're solving for angle T, and we have every other number in the formula. So we have a lot of computation to do and a fair amount of algebra. You're going to have to be pretty good at algebra to have success here because there's steps that have to be done in the right order, in the right way. So if you trust me here, I'll skip some steps. 81 should equal 85 minus quantity of 84 cosine of T. Subtract 85 from both sides. You get negative 4 equals negative 84 cosine T. Divide by negative 84 on both sides. You get 1/21 equals cosine of T. Now we do inverse cosine to find the angle. Inverse cosine of 1/21 gives us that T is approximately 87.3 degrees. There's our angle. So you can use the law of cosines to find angles in a triangle where the three sides are given to you. Next example. We have a triangle where we're given two sides, 7 and 8. We're trying to find an angle, theta. If you tried to use the law of cosines, you would find that it won't work. We just don't have the right information given to us. We'd have too many variables. Plus, the law of cosines is only good for side angle side and side side side. This is neither one of those. This is side, side, angle. Notice the angle is not the angle that's in between the sides. This is an angle beyond that. So because we're given side, side, angle, this will require us a different kind of a law, and this different law is called the law of sines. Law of sines works great for side, side, angle. And it says something like this. The sine of an angle A over the opposite side A is equal to the sine of another angle, B, let's say, over its opposite side, which is B. And of course, it would be true for the third side. Of course, you only need 2 of these to make a proportion, but it would also be true for the third side and the third angle. So you can use any two of these to set up a proportion. Once you set up a proportion, then you should be in business from junior high math. So for this triangle, it would be the sine of theta over the side opposite that, which would be 7. Set that equal to the sine of the angle that's 40 degrees divided by the side that's opposite 40, which is 8. Now we cross multiply. We'd get 8 times the sine of theta equals 7 times sine of 40 degrees. Divided by 8 on both sides. That'll give us the sine of theta equals that fraction up there. And if you type that in and do inverse sine on both sides, you'll find out that theta is approximately 34.2 degrees. So we use the law of sines this time to set up a proportion and solve for the missing angle. Law of sines, again, is good for side-side angle. It's also good for angle-angle side. It's also good for angle-side angle. So there's 3 scenarios where the law of sines would be the appropriate measure. So there you have it. There's the law of sines, law of cosines. One other kind of weird thing, though, is the situation where you could have an ambiguous case. You can read about the ambiguous case in your textbook, but I do have some drawings down here. Oh yeah, number 6 is an extra problem that you can do, as well as your homework. It's very important that you practice this before you take any quizzes on this. But here's the ambiguous case. It's a case where you can get 2 different triangles out of the same information. So for instance, if I passed out compasses and rulers and I said, all right, side AC has to be 10.5 inches, side AB has to be 6 inches, and angle C must be 31 degrees or something like that. If you were required to build a triangle with those 3 pieces in those 3 positions, it turns out that, of course, you can make the big triangle, but when you swing your compass around with that distance of 6 inches, your compass can actually hit in 2 places. It can hit down in the bottom right and make a triangle ABC, but it also hits in another spot. There's another place where the side can be 6, creating 2 places where point B can be. Point B can be toward the left, or point B can be toward the right, and we end up having 2 complete triangles, both of which you would have to solve using law of sines or law of cosines. So it means you're going to have a lot of extra work. However, the only time the ambiguous case could ever happen is if you have side-side angle given to you. And it has to be kind of given to you in a particular way. In other words, not all side-side angles are going to be ambiguous, just the ones where the 6 or the smaller side somehow is able to be swung with a compass across and hit in another spot. So you almost kind of have to have a savvy with compasses and straight edges to imagine when that would happen in a triangle. You'll have to kind of sketch it, kind of have to draw it to scale, which you should be able to do if you've had a year of geometry. You ought to be able to draw a triangle to scale. And so if that third side, or that second side, the smaller side, is able to be swung across and hit twice, then you've got yourself an ambiguous case. It doesn't happen very often, but if it does, then you'll have to solve both triangles. So there you have it. There's lesson 7.1. I know I went kind of fast, but if you have any questions, bring them to class. I'll see you then.